Hi, folks. Having some technical difficulties today. So, what this is Wednesday. So, we're not meeting today, but I did want to send you a video that I'll upload as soon as I can get my hardware working the way it's supposed to. And I'll show you when we get back together how to find these. But I didn't want to leave us with no additional information. So, let's see. We left off last time talking about angles in radians and converting them. And we looked at our standard angles for our, I will have to get better at that. Our standard angles going around our circle. So in radians, we said we go from 0 to 2 pi in one full rotation. That meant it's pi radians to get halfway through a rotation. Then half of that would be pi over 2. It's equivalent to our 90 degrees. And then we went pi over 4. And then from there, we counted around. And this is something I really do want you guys to practice. I want you guys to essentially be able to go through this construction on your own as soon as you can. So if we were to count this around, that would be 1 pi over 4, 2 pi over 4. And as we talked about, that 2 pi over 4 could then be reduced back to that pi over 2. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which would again reduce, 5 pi over 4. We could go 6 pi over 4 here, but that will reduce to a 3 pi over 2. So we're going to do that. But that was 6 pi over 4, then 7 pi over 4, and 8 pi over 4. Of course, 8 pi over 4, like the others, would reduce to that 2 pi. So that gave us the pi over 4s. If we wanted to, instead of cutting this into half again and getting pi over 8s, which we actually don't want pi over 8s, we'll talk about why in a little bit, but if instead of cutting this pi over 2 in half, we cut it by a third of a half gave us that pi over 6, and then we could count pi over 6s all the way around in the same way. So that would be 1 pi over 6, 2 pi over 6. I'm going to write it up here because we will reduce it in a minute. Then 3 pi over 6. 3 over 6 would reduce to the 1/2. 4 pi over 6. 5 pi over 6. And 6 pi over 6 reduces to that pi. Then we could count 7, 8, 9, 10 pi over 6 and label those the same way. 7 pi over 6, 8 pi over 6, which would reduce to 4 pi over 3. 9 pi over 6 would reduce to 3 pi over 2. 10 pi over 6 would reduce to 5 pi over 3. And 11 pi over 6 before reaching 12 pi over 6. And again, that 12 pi over 6 is going to reduce back to that 2 pi. So we usually just stick with the 2 pi. So we went through this construction real quick. I think it looked better to practice that. But we went through this construction real quick at the end on Tuesday, and you do want to, yesterday, and we do want to practice this as much as we can. We want to get a sense of this intuition. We will consider these angles to be our standard angles in radian measure. They are equivalent to, if we want to do it instead in degrees, and make those straight so they a little tighter. So if we wanted to do them in degrees, it would have been equivalent to 0 to the 360 degrees. Net half rotation's 180 degrees. So 180 degrees and pi radians are the same measure. And then half of that's 90 degrees. Of quarter, that's 45 degrees. 45, 90, another 45 to 135 degrees, and so on along the circle. These are the angle measurements that we are relatively familiar with, depending on your background. And we could break it up, instead of breaking it up in half to get the 45, we could break it up into thirds. A third of 90 is 30 degrees. So again, 30 degrees is the same angle measure as this pi over 6 radians. That pi over, oops, we didn't even reduce that. That pi over 3 is the same as 60 degrees, and so on around the circle. This, which we usually reduce to 2 pi over 3, I know we did that yesterday, would be equivalent to, well, that's 30, 60, 90, so that would be 120 degrees and 150 degrees, and so on around the circle. And so these angles are the same whether we measure them in degrees or in radians, and they do form our collection of, again, standard angles. Why is this 210? That's 210. There's nobody here to correct me when I say things like that. This would be what, 225 degrees, sorry. 45 added to the 180. And then that's what? Now I'm all nervous. That's 240 degrees, 300 degrees, 330 degrees, and 360 degrees. So in radians, these are the standard angles we work with. In degrees, these are the standard angles that we work with. But it's important to keep in mind they are the same angle measure. We're just in here labeling them in degrees, and over here labeling them in radians. We talked last time about converting degrees into radians. If you want to go rewatch that, I posted the video that we recorded when we talked on yesterday, on Tuesday. Well, on Tuesday, depending on when you're watching this. So why these angles are more important, we'll talk about a bit next week. It's because of some of the geometry associated with these angles. It's not that 30 degrees is somehow, more magical than 20 degrees or 10 degrees, except that there is some very handy geometry associated with 30 degrees, 45 degrees, and 60 degrees that make them really handy for us to use for a lot of things. And again, we'll talk about that at the beginning next week. We got to this point of talking about radian measures and having them be handy by discussing wanting to have a handy set of tools for measuring angles that would be more meaningful. And I want to show you one of the big reasons why it's as meaningful as it is. So if we go back to our definition of an angle in radian measure, theta, and we recall that that's equal to the arc length divided by the radius of the circle it's inside. So just to remind you, if we have a circle that is a terrible circle, well, you want a circle, frankly. If we have a radius and that radius goes through some arc length, S, so this is curved, it's a circle, part of a circle anyway, then this radius and that radius would be the same because it is on a circle. And this angle, theta, is in radians the ratio between that arc length and that radius. We looked at some examples the other day where if this arc length was, say, 7 and that radius was 5, then that angle measure in radians would be the ratio between them, 7/5 radians. Because these are both whole values, there's no pi in this. Remember, pi doesn't have to be in your radian measures. If it's not, like this one's not, that just means that this arc isn't an even cut around a circle. You couldn't have a whole number of these arcs make a circle. That's okay. It doesn't have to be a whole number cut. It's an irrational cut. Radiuses and arcs are often connected through that irrational number pi. But it doesn't have to be there to be a radian measure. So this was our definition for radian measure. And with just a little manipulation, multiplying both sides of this by r, and then I'm going to write it as S equals r theta, we get a very nice handy formula for arc length. This formula tells us if we want to know some arc length S, if we know the radius of the circle, again, I'm just going to make this 5, and we know this angle measure in radians, I'm going to say it's 0.8 radians. I'm going to label it radians. Then if we want to know what this arc length is, again, assuming this is a circle, then that arc length is going to be just that product of the radius times the 0.8 times the angle measure in radians. So that arc length is what, 5 times 0.8 is 4. And if this is inches, then inches times radians is just inches. We talked the other day about that radian measure not being a unit that contaminates things. So we do get to multiply that 5 inches by this ratio, because radians is a ratio unit. That ratio doesn't add any units. So our 5 inches stays in inches. If we tried to compare this to doing the same problem in degrees, let's say we had a radius of, I don't know, say 9, and this angle instead, we were told it was 60 degrees. If we tried to use the same formula to find the length of that arc, S equals r theta, and tried to use this 60 degrees, we'd have our 9, and again, we're going to call that inches, that 9 times 60 degrees, and our result would say that the length of this arc is 540, 9 times 60, 540 foot degrees. I don't know about you, but I don't really know what a foot degree is. Or we could leave the degrees here and say 540 degree feet. I still don't know what a degree feet is. And certainly if this is 6 inches, this isn't 540 inches at just 60 degrees. This formula, it's a very, very nice formula, but it only works because of that structurally meaningful definition of that angle in radians. But the nice thing is we now know how to convert that degree measure into radians. So instead of working in degrees, because these formulas won't work in degrees, we can either do our conversion. Again, if you need help with the conversion, look at that video from Tuesday. But if we even just remember from what we did a couple of minutes ago, that 60 degrees was pi over 3 radians, then instead of using the 60 degrees, we can go over to this formula and say our arc length, it's still r times the angle, but now that this angle is in radians, it'll work. So that 9 times pi over 3 is, those 3's cancel, and we get 3 pi, but 3 pi watts? 3 pi, this 9 was inches. This pi over 3 was radians, but again, radians don't contaminate. So it's 3 pi inches. And we could just leave it right there. 3 pi, pi is a nice irrational number. It's about 3.14. So 3 times 3.14 is going to be, what, somewhere around 10. I suppose I could find out here. 3 times pi, 9.42. So we could say this is about 9.42 inches. But frankly, this 3 pi inches is a great answer. Leave it alone. It's easier to say 3 pi as opposed to say 9.424777961, blah, 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 blah. So, it's great conversationally to have that 9.4 so we can have a sense of size. But the 3 pi is frankly a nice, easy answer. So we could just say the arc length is 3 pi inches. And that's a perfectly good and reasonable answer. Do make sure when you're doing homeworks and tests and quizzes that you look and see what form it wants. If the computer asks for it rounded to 2 decimal places, make sure that's what you give it. But if it asks for exact answers, leave exact answers. And do make sure you're doing your rounding as late as possible, so you don't compound your compound any rounding error that happens. So yeah, this arc length formula is a super, super handy formula, and it becomes especially easy because we are in a radian measure where this measure is already in the units that we want it to be in. Now, real quick before I let you go, I want to make these short so you guys can watch them pretty quick. There is a slight modification to this formula that gives us something that's in some ways even cooler. If we take each of these and divide our arc length and our radius by time, and consider this arc length to be a circular distance over time, so some velocity of something going around a circular arc, and that circular arc is still going to have a radius of r. But as it goes through this arc, the angle here is going to change over time. So we're going to imagine kind of dividing both of these by time. So say this again was in inches, or say feet. Feet divided by seconds would be feet per second. Feet per second is a velocity, a linear velocity along that arc. That radius, again, if this is going to be feet per second, then this radius, let's call it feet. And then this radians per time, so it's still in seconds, this is radians per second. If it was in degrees, it would be degrees per second, an amount of rotation. But for this formula to work, we're going to want this to be radians per second, radians per time, whatever the time unit happens to be. We're using seconds here as an example. And radians per time, the symbol we use, it looks like a W, but it's actually the Greek symbol omega. If you call it a W, no one's going to argue with you, or most people won't argue with you. I might remind you it's an omega, but so linear velocity is equal to radius times angular velocity, how fast it's turning, or sometimes we just say angular speed. So this gives us, instead of how far do things go as they turn, it's how fast do they move as they turn. So example, if something is, say, moving here at a nice linear speed of, say, 10 feet per second, that's fairly quick, actually. If you're riding a bicycle, 10 feet per second is pretty reasonable, pretty even pace. So you're going 10 feet per second along this curve, and let's say this radius is 20 feet. So a reasonable question would be, well, how fast is this angle growing? Well, this relationship will give us that. So if we have a velocity of 10 feet per second, okay, 10, and we can even put in feet per second if you want, equals 20 times that angular velocity, omega, that we want. So divide off the 20. That's going to give us 1/2 equals omega. So that's an angular speed of 1/2 radians per second. So we turned that angular speed, turned that linear speed of 10 feet per second into an angular speed of 1/2 a radian per second and got an angular speed. Now, that 1/2 radian per second might be hard to visualize because we're not used to thinking in radians yet, but we'll get better at that with practice. But if we wanted to turn this radians per second into either degrees per second, we could. Let's do that real quick. Again, just like we did for converting, if we want to get rid of radians, we're going to have to divide out the radians and put in the degrees. That'll turn us from radians into degrees. So we know our equivalency is 180, that's an 80 degrees in pi, started to put 2 there, in pi radians. So that would be, 1 times 180 degrees is 90 degrees divided by pi. So that's degrees, the radians are gone, the per second is still there, so per second. So it might be nice to know what 90 divided by pi is. That should be somewhere in the realm of 30, but let me find it. 90 divided by pi is 28.6. So our angular speed is 28.6 degrees per second. So if that's easier to visualize, great. You can visualize that turning at 28 degrees every second. If we didn't want to think in degrees per second or in radians per second, we often talk about things spinning in terms of RPMs. You've probably all heard about RPMs. RPMs stand for rotation or rotations per minute. So if we want to take this 1/2 radians per second, and I'm going to go back to the 1/2 radians per second. I'm actually going to write it as 1 radian every 2 seconds, just to have a nice fraction there. If I want to turn that into rotations per minute, we just have to turn radians into rotations and seconds into minutes. So just like we did with the degrees, I'm starting to go at an angle here. We want to get rid of radians and put in rotations. So again, just like knowing that these two things are equal, that 180 degrees and pi radians are the same, we'd have to know an equivalency between rotations and radians. And luckily we do. We know 1 rotation is the same as 2 pi radians. That's going to make the radians cancel and turn us into rotations per second. So if we wanted it in rotations per second, how many times does this thing spin around every second? We'd be good. But RPMs go to per minute. So again, we want to get rid of seconds. So we got to put seconds on top this time so they'll cancel. We want per minute, so the minute's got to go on the bottom. And again, we have to know an equivalency. And we certainly know 60 seconds is the same as 1 minute. Our seconds are going to cancel, and we'll be left with rotations per minute. We'll be left with RPMs. So 1 times 1 times 60, 60. 2 times 2 pi times 1 is 4 pi, and it's 4 pi rotations per minute. We could reduce that real quick to 15 over pi RPMs. And 15 divided by a little more than 3, so there should be a little less than 5. Again, we'll find out an approximation just for the fun of it. Again, we don't need these approximations. 15 over pi RPMs is a perfectly reasonable answer. But if you're trying to describe it to somebody, saying 4.77 RPMs, will probably be more helpful. So this is just, RPMs, that spinning things like spinning flywheels, or you often see, problems with a Ferris wheel. You're given the radius of the Ferris wheel and either how fast it's spinning or how fast the cars are moving. If we know the radius of that Ferris wheel, say 20 feet, if we know how fast this is spinning in either radians per second, degrees per second, or RPMs, we could turn any of those into radians per second. It's always nice if we're told radian per second, but that doesn't happen very often. But any of these, we can do a little of this dimensional analysis to turn it back into radians per second. That radians per second goes into this really nice little formula, multiplied by the radius, and we get the speed of the cars. If you know the speed of the object, the linear speed, the velocity of the object around the curve, and you know the radius, well, then we can go this direction. It does take a little bit of practice, and you get a chance to practice some of these on your homeworks. If they give you any trouble, let me know. This does tend to be a really good thing to practice. We will use it fairly often. So make sure you practice this and ask any questions if you have them. All right, I think I'm going to end this here just so it's not too much to intake all at once. I know I've been talking a lot and talking pretty fast. Please let me know if you have any questions about any of this. I'm sure it will come up. These could be a little bit tricky sometimes, particularly with all this dimensional analysis in here. That might be something you haven't used in a while and that you need to practice. So practice with that. Let me know how it goes, and have a wonderful day.